All right, today we're going to tear apart the architecture of a brand new, super high performance time series database that's built in Rust. We're going to see what makes it just so incredibly fast.
I mean, just imagine trying to capture a literal avalanche of data, a constant stream that never, ever stops. We're talking millions of data points every single second. How in the world could you store all of that and still be able to ask it questions in real time?
Well, that is precisely the problem that a time series database, or a TSDB, is built to solve. And today, we're digging into a really fascinating new one called RusTs. We're going to follow a piece of data right through the system and see exactly what makes it tick.
Okay, so first things first, what exactly is RusTs? Let's get the basics down.
At its core, a time series database is just built for any kind of data that has a timestamp. See, the whole point isn't just to store the data, but to make asking questions about it based on time insanely fast. This is really the bedrock for everything from modern system monitoring and IoT to financial tech.
So Rust comes out of the gate with some pretty big promises. We're talking extreme performance, really clever compression to save a ton of space, and the ability to scale out across a whole bunch of machines. It's also compatible with the InfluxDB line protocol, which makes it way easier for people to give it a try. All right, so does it actually deliver? Let's find out.
To really get what makes Rust's tick, we're going to follow one single data point on its journey through the system. This is where we get to see all the smart design choices that are all about speed and safety.
So picture this. One single sensor reading, it just hit the database. What happens right now in these first few milliseconds? This little journey, it tells us everything about the system's philosophy.
The first part of its journey is this little three-step dance. First, the data hits the API. Then, boom, it's immediately written to a special log on the disk for safety. And only then is it put into a super fast buffer in memory so you can query it right away. Let's really dig into those last two steps.
The write-ahead log, or the WAL, is basically the database's insurance policy. I mean, before anything else happens, the data gets scribbled down here. So if the server just poof goes down, Rust can just replay this log when it starts back up. Not a single data point lost. It's all about that durability.
But of course, that kind of safety has a cost: performance. So Rust gives you control over that trade-off. You can force a sync to disk for every single write if you need maximum safety, which is perfect for financial data. Or you can sync every so often for a nice balance. You can even just let the operating system handle it if you want the absolute highest throughput. It's basically a dial you can turn, choosing between pure speed and absolute bulletproof safety.
Okay, so after the wall, our data lands in the mem table. You can think of this as the system's lightning-fast short-term memory. Since it's all living in RAM, any questions you ask about the most recent data get answered in a blink. This is what gives you that incredible real-time feel.
Okay, so our data is safe in the wall and it's super fast to query from the mem table. But, right, memory isn't infinite. What happens when that buffer gets full? Well, this is where things get really clever.
Once that mem table is full, its contents get flushed out to permanent storage on a disk. Now, just dumping the raw data would be super inefficient. So this is where Rust unleashes its secret weapon: compression algorithms that are tailor-made for the weird, specific patterns you only find in time series data.
And wow, look at these results. They're just nuts. We're talking about timestamps being compressed by 10 to 15 times their original size. Sensor readings shrinking by 8 to 12 times. This isn't just about saving some disk space. This is what makes storing just mountains of data actually affordable. So how on earth does it do that?
Okay, for timestamps, Rust uses this thing called delta of delta. Think about it. If your data comes in every single second, the gap between timestamps is always, well, 1 second. So the change in that gap is 0. The system basically ends up storing a massive list of zeros, and you can imagine how well that compresses.
Now for numbers, it uses Gorilla compression. This came out of Facebook. You know how sensor readings like temperature don't usually jump around like crazy? They just change a tiny bit. Gorilla is super smart about this. It only stores the few bits that actually changed from the last reading. It's an incredibly efficient way to handle this kind of data.
So we've got all this data stored away, super compressed, awesome. But writing fast is only half the battle, right? It's pretty useless if you can't get that data back out again just as fast.
So the big question is, how do you find that one tiny needle in a petabyte-sized haystack and do it in milliseconds?
The secret sauce here is a really cool data structure called a roaring bitmap. Forget about searching through a phone book page by page. This is more like a super fast Venn diagram. When you ask for data from, say, host equals server 1 and region equals US East, it can instantly find where those two circles overlap. It tells the database exactly where to look on the disk before it even starts reading the data. It's just incredibly efficient.
All right, everything we've talked about so far is amazing on a single server. But what happens when you've got so much data that one machine just can't cut it anymore? Now we're talking about distributed architecture.
Yeah, for truly massive planet-scale workloads, you have to scale out, not just up. And RusTs Mist Data does this using two classic tricks of the trade: sharding, which is all about splitting up the data, and replication, which is about making copies.
Sharding is how RusTs divides your data across all the machines in a cluster. And what's cool is that you actually get to choose how it's split up. You can spread it out evenly, you can keep related data together, or you can even split it by time. Having this kind of flexibility is a huge deal because it means you can tune the physical layout of your data to perfectly match the kind of questions you ask it the most.
Then there's replication, which is all about making sure you don't lose data if a machine dies. And just like with the wall, Rust gives you another one of those dials to turn. You can use synchronous replication for that super strong consistency you need for financial data, where losing even one transaction is a total disaster. But for something like high-volume metrics where you just want to fire and forget and speed is king, you can go asynchronous. It's all about matching the guarantee to what you're actually doing.
So when you look at the whole picture, from the write-ahead log ensuring safety, to the wild compression, to those clever roaring bitmaps for instant lookups, every single piece of Rust is engineered from the ground up to handle time series data with brutal speed and efficiency. You know, it really makes you wonder, with designs this laser-focused, could Rust really be the future of high-performance databases? Thanks for diving into this with me.